Okay, continuing with the circles, we've talked about central angles, and in this section we'll talk about inscribed angles. The big difference between an inscribed angle and a central angle is this. Look at where the vertex of the inscribed angle is. It is on the circumference. So I'm going to construct another circle here. Alright, and then well, it doesn't look very circular, but just pretend it's a circle, and we'll say circle center C, and I'm going to plonk 2 points here. Let's call them X and Y. That X just looks a bit sorry. In fact, now it's looking even sorrier. So let's try that again. So this is X and Y. If I connect X to C, okay, and connect X to C here, this red angle is the central angle. Central angle is formed at the center of a circle. Its vertex at the center of a circle. An inscribed angle is on the circumference. Inscribed angle. Okay, and the inscribed angle has two sides, and where the sides intersect the circle, that part of the arc is called the intercepted arc. Okay, inscribed angle, intercepted arc. What is the measure of an inscribed angle? So there's a theorem here which says the measure of an inscribed angle. So this is your inscribed angle here. Inscribed, which is called ADB, is half the measure of the central angle, or it is half the measure of arc AB, the intercepted arc. So over on the side, let's just say that the measure of arc AB is 100 degrees. That means that all right, one more. That means that this angle is 100 degrees. Measure of arc AB equals 100 degrees. And since the inscribed angle is half of that, then the measure of the inscribed angle is going to be 50 degrees. The inscribed angle is always smaller than the central angle of the intercepted arc. Okay, now the way you can form an intercepted arc is there are three cases. In the first case, you see that the center C is on a side of the inscribed angle, so this is your intercepted arc. In the second case, the center C is inside the angle, so that's your intercepted arc. And in the third case, the center C is outside the inscribed angle, that's your intercepted arc. And this is just so that you are not thrown off when you see it either way. And by the way, in the first case, this is a semicircle. The measure of this arc, let's call it PQ, is 180 degrees because that's a semicircle. Okay. On our journey of inscribed angles, if two inscribed angles of a circle intercept the same arc, so you've got angles D and C, which are intercepting arc AB. Or you could think about it this way: angle ADB and angle ACB have the same endpoints AB on the circle, and these are inscribed angles. And what we are saying is, if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So if measure of A, let's get out of the highlighter mode. So if the measure of arc AB is 60 degrees, then the measure of angle ADB will equal the measure of angle ACB, which will be half of the measure of the intercepted arc, so that will be 30 degrees. But look at these two angles are congruent. Inscribed polygon. Inscribed means that the vertices of the polygon lie on the circle. So first you have a polygon with a minimum number of sides, 3, and that's a triangle. So here we go, 1, 2, 3 vertices. So you have an inscribed angle. Okay. The next one, okay, there is a typo here. There should be a T in here. The circle that contains the vertices. The circumscribed circle is the circle that contains the vertices. Okay, so here we go. We can even name this one. And you always go in counterclockwise or clockwise order. So this is A, B, C, D. And you will soon see, you know that the sum of the angles of, interior angles of a triangle is 180. And the sum of the 4 angles of a quadrilateral is 360. And that was just a freebie thrown in there. Next, let's look at this diagram. We have a diameter. Diameter. So if that is the diameter, then that blue arc is as a semicircle. Its measure is 180. So let's write that down. Measure of arc AC equals 180 degrees. And we just learned the theorem that the inscribed angle, which is angle ABC, will be 90 degrees. In fact, we can indicate that, can't we? Okay. So the theorem says if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. So if you start off with a right triangle, then you can assume or conclude that the hypotenuse is diameter. Conversely, if one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter is a right triangle. This is fairly intuitive. Next theorem, and I alluded to this briefly. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. I lie, I did not allude to this briefly. What I did allude to it is that the four angles of a quadrilateral add up to 360. Alright, this theorem is saying that a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So that means measure of angle F plus measure of angle D equals 180, and measure of angle E plus measure of angle G equals 180 degrees. This makes a lot of sense, because if you think about it, this arc EDG plus this arc EFG, they add up to 360 degrees. Their measures are 360. And since angles EDG and EFG are the inscribed angles, their sum will be half of 360, which is 180. So this is useful in figuring out angle measures given a circle and given that a quadrilateral is inscribed in a circle. So now you have some example questions here. Find indicated measure in circle C, measure of angle D. Okay, so go ahead and try these. And I don't think you should have any trouble with that. All right, good luck.
Oh, okay, I have a simple thing. You want me to do that?